Alright, so now let's talk about conservation of heat energy. Now we already know that energy is conserved in the universe, that energy cannot not be created nor destroyed, but it does change forms from one to another. Now in this sense, it's never changing forms. We are only dealing with heat, but it is still conserved. The same way that if I give you $5, well, I may have lost $5 and you may have gained $5, but we did not create any dollars. The same amount of money was floating around both before and after that transaction. Similarly for heat, anytime something gains heat, it's getting it from something else. So something gained heat and something lost heat, and altogether there was no heat created or destroyed. This is put simply by just saying the sum of Q is 0. If you add up all of the heat gains and losses, they must equal 0. You can gain some, you must be also losing some, and at the end of the day, the net is 0. And we've seen the two equations that we work with. We use Q equals mc delta T to compute changes in temperature, and the sign of this is automatically determined by delta T. This Q is positive if T increases, final minus initial. If the final is bigger than the initial, it's positive. Or it's negative if T decreases. If you end up at a final temperature lower than where you began, final minus initial is negative. But either way, you don't really have to worry about it or think about it. Delta T will give the sign here. Just make sure to always use final minus initial for delta T, and the sign will be correct on Q for Q equals mc delta T. The other way in which we have to keep track of keep track of heat is in phase changes. Q equals ml is our equation for changes in phase, and it is positive when you add heat, just like you add heat and something's temperature increases, you add heat to melt or boil it. It's positive when you add heat. It's negative when it releases heat, similar to something lowering its temperature. That is when you freeze or condense something. But there's no delta T in here to determine the sign. Only the mass, which is a positive number, and the L, which is a constant. You have to give the sign here based on the situation. Again, it is positive if you're adding heat. Just like if you would add heat, it increases something's temperature. It's negative when releasing heat or taking heat away, just like this would be negative if the temperature decreased. In that sense, it's easy to remember, but it is a little tricky that one of these, the sign naturally just happens on its own, and for the other, you have to make sure you give it the correct sign. So let's work an example. I say there are 30 grams of ice starting at 0 degrees, freezing temperature of water. Ice could actually be even colder, and in that case you have to heat it up before it melts. But this ice is right at 0 degrees, it's right on the fence. It just needs a bump to go from solid to liquid. We have 30 grams of ice at 0 degrees is added to an insulated cup, meaning the cup isn't going to affect the problem at all, containing 300 grams of water at 30 degrees Celsius. What is the final or equilibrium temperature? So, I would first like you guys to kind of talk through these problems in words. Well, what's going to happen? We've got warm water, 30 degrees Celsius, that we put a cup of ice into. That warm water is going to get colder. Well, if its temperature goes down, that's going to be negative. The ice is going to melt. Well, it's gaining heat. If it's melting, that's going to be a positive ml term. And then what's going to happen to the ice once it melts? Well, that ice water is then going to warm up. And if that ice water is getting warmer, we're going to have a positive Q equals mc delta T. So let's now write that down in equations. So setting this up, we're going to have an mc delta T for the warm water cooling. We then have an ml, and it's going to be an mlf because we're crossing the solid-liquid boundary, but I indeed do want that to be plus because the water is melting. It's having heat added to it, so this is a positive term. And then my last one is going to be, ice melting. My last one is going to be MC delta T. For now, we're going to have ice water after the ice melts. And that ice water warms up. And we know all of this should equal 0. That the amount of heat that the warm water loses is going to be equal to the amount of heat that melted the ice and then warmed up that ice water. And so let's go through here and be a little bit more careful as well. I'm going to call this M1. And this will both be M2 because M1 is that warm water. I had 300 grams of M1. M2 is the ice. I only had 30 grams of ice, and then it becomes ice water. Ice and then ice water. The 300 grams is the warm water. For all of these, C equals 1 calorie per gram degree Celsius. An easy number to remember. But we're both warming up water, having warm water cooling, and then cold water warming up. Both cases it is water, which means we use C. And then what about those temperatures? Well, we know that the ice, what we'll call T2 initial, is 0 degrees. T1 initial is 30 degrees. And T final is shared by everything. It's the equilibrium temperature. Everything has the same equilibrium temperature. All right, so we set up our equation. We've now got all of our knowns to plug into it. Let me write this out in numbers now. So M1, 300 grams times 1 calorie per gram degree Celsius times T final minus T initial for the warm water was 30 degrees Celsius. Then plus, I would have 30 grams of ice. Water melting, the LF, the latent heat of fusion, is 79.7 calories per gram. And then I have 30 grams of ice water. So it has a C of 1 calorie per gram degree Celsius times T final minus T initial is 0 degrees Celsius. And all of that should equal 0. Now this is going to distribute. Here we have 300 times 1 on the outside will multiply T final, and it will multiply negative 30. These two numbers will combine. Here we won't have to distribute because T final minus 0, well, that's just T final. So this is going to get a little messy in this step and then clean up nicely at the end. Multiplying 300 grams times 1 calorie per gram degree Celsius, the grams cancel, and I have 300 calories per degree Celsius times T final minus, I can multiply all of this together, 300 grams times 1 calorie per gram degree Celsius times negative 30 degrees. All of that becomes negative 9,000 calories. I can multiply 30 grams times 79.7 calories per gram. That becomes 2,391 calories. And then what I have left over here is 30. The grams cancel. I have units of calories per degree Celsius times T final. And all of that should equal 0. Well, I have 300 calories per degree Celsius T final, 30 calories per degree Celsius T final. Those pieces combine 330 calories per degree Celsius times T final. I have negative 9,000 plus 2,391. That is negative 6,609. I can add that to the other side. So I have 6,609 calories. And then lastly, I've run out of space, so I'm going to grab one extra piece of paper. 330 calories per degree Celsius times T final equals 6,609 calories. We divide by 330 calories per degree Celsius on both sides. I have calories over calories per degree Celsius. This is like calories over 1 times degrees Celsius over calories. I'm going to get an answer in degrees Celsius. And whenever we divide 6,609 by 330, we get 20. The final temperature is 20 degrees Celsius. But once more, just recapping what we did in that example. We first set up in words what was going to happen. The warm water was going to cool down. The ice was going to melt. That ice water would then warm up. We added up all our different Q's, all the different pieces of heat energy, and they must have equaled 0. And I kind of skipped that last step of adding things over. We really had 330 calories per degree Celsius times T final minus 6,609 calories equals 0. We add that 6,609 calories to both sides. That is where that got over to the right side. But this is a classic example of keeping a balanced budget for conservation of heat energy. And we'll use this again and again in many different contexts. Our last example will be determining an unknown substance. This will be very similar to what you will be doing in the lab.